Hello, everyone. Welcome to 5 Bull Cram Safety Physics, Night 2. We'll wait a couple minutes for a couple more people to come in, and then we'll get started. All right, I think we're ready to get started now. So first up is a review of our cram schedule. Yesterday was units 1 and 2. Today's units 3 and 4. Tomorrow we'll do 5 and 6. May 9 we'll be doing unit 7, and May 10 will be our finale. I'm one of your hosts, Juliana, and I will be doing unit 3, which is circular motion and gravitation today. And I'll call my other hosts down to introduce themselves again to you.
Hey guys, I'm Anastasia, and today I'll be teaching the work unit.
Everyone, my name is Shagun, and I'll be, I hope you guys remember me from yesterday from teaching dynamics. Today I'll mainly be on the backstage chat, so if you guys have any questions, just direct them to me. And tomorrow I'll be teaching momentum.
Hi guys, my name is Zeke, and today I'm going to be going over energy with you guys, especially mechanical energy and the conservation of energy.
Hey everyone, I'm Tammy. I'll be back tomorrow for momentum and simple harmonic motion. Oops.
All right, and don't forget to follow at Think5 on social. And then moving on, tonight is night 2, and we're doing units 3 and 4. So our agenda is we're going to do unit 3 on circular motion and gravitation, which is around 6 to 8% of the exam. We're going to go over a couple of MCQ and FRQ questions. And then we're going to do energy, which is a big part of the exam at 20 to 28%. And then we're going to do a couple more MCQ and FRQ questions. So just some tips on how to make the most of a cram finale. Notes, take a couple reminders, use mnemonics, questions, study to-do list, but don't try to write everything down. If you need it, Cram Hub, which is the green button down below, has all of the slides in the review packet and the replays for you, which will be immediately available after this event. The group chat is for sharing tips and tricks and just chatting in general. And the Q&A tab is where you can ask any question about the exam, and we will answer you later, or we will get back to you in the comments. Yes, we will take a break around the middle, around like the 8:30 mark actually, and a replay will be available immediately after the event. All right, so just a few agreements. Be supportive of each other, be patient, and be kind. And finally, just a heads up about our competition. You can win $100 by sharing your cram experience on TikTok and Instagram, and the details are in our slide. And I'll give you a couple seconds just to read that. Okay, so moving on to content. Unit 3, circular motion and gravitation. So the first thing you have to know about mapping gravitational and circular motion is that it typically depends on where you are relative to other objects in the system. So of course you remember from our last night and just AP physics in general about free body diagrams. So free body diagrams map forces acting on one object or system at one position or time. In contrast, vector fields, which we usually use in circular or gravitational movement, map forces on other vectors at multiple positions or times. So basically, a free body diagram is for one time and a vector field is for multiple times. You don't usually see the term vector field on the AP exam, but you do need to be able to draw basically a free body diagram at different positions. So this is how you sort of use vector fields. And vector fields in Physics 1 are used to display circular motion and gravitational attraction. So the 4 fundamental forces of AP Physics and physics in general are the strong force, which binds particles of matter together. So this is what connects protons with neutrons. The electromagnetic force, which conveys positive and negative interactions. The electroweak force, which is involved in radioactivity and particle decay. And gravity, which is the attraction between two objects in mass. I'm seeing a question that asks, do we have to draw vector fields for FRQs? And I would say no, you wouldn't typically have to draw one, but you might have to draw a free body diagram at multiple points and make sure the forces are pointing in the correct direction. Vector fields typically do show up in AP Calc though. And then the only fundamental force that we typically use in AP Physics 1 is gravity. And the reason this is because the other 3 forces do not really work at large distances, and they're only applicable at like very small or specific ranges. The one exception to this could be electromagnetic force, but this is typically covered in Physics 2 and Physics C. So in gravity, in AP Physics 1, we're only really going to talk about gravity as a non-contact force, or basically the only force that doesn't need to touch an object to act on it, because it works on all objects with mass, no matter the size or distance. And it can work over really long distances. We will only be using gravity on the test, and you probably won't be using much of the fields. It's just an intro to the topic. All right. So these are the two equations for gravity. The equation for force is the gravitational constant times the mass of the first object times the mass of the second object, all divided by the distance squared. So this means that gravity is directly proportional to mass, so it increases as mass increases, and inversely proportional to distance. So that means that gravity decreases, or the force of gravity decreases as the distance increases. This equation is called Newton's law of gravitation and applies to all objects. Big G is a number, while little g is just a way we represent acceleration. So little g would equal negative 9.8 meters per second squared on Earth, and it will be a constant depending on whatever planet you're on. And then big G is an actual number they give you on the test, but you don't have to write it out. So acceleration, which we usually represent with a small or lowercase g, is equal to big G, or the gravitational constant, times mass divided by r squared. And you'll notice here that only m1 is included, which would be the mass of the planet, or like the larger object. Like we know on Earth, acceleration due to gravity will always be constant no matter what object is falling. So that's represented in this equation by only one mass being involved in the equation, which is the mass of the planet. This number also represents gravitational field strength, but they're probably not going to ask you that on the test. All right, now moving on to centripetal force and uniform circular motion. UCM, or uniform circular motion, occurs when an object travels in a perfect circle without changing its speed. So the object is changing its velocity because velocity is a vector. A vector is composed of magnitude, which is typically the speed, and direction. So this means that the object is changing which direction it's moving, but it's not changing its actual speed. At any position of uniform circular motion, velocity will be tangent to the circle edge, this circle representing how the object is moving, and acceleration will be towards the circle center. Centripetal force is considered a net force, not a type of force. So any force like gravitational, tension, friction, or normal force can cause centripetal motion and be considered the centripetal force, but you wouldn't label a force as centripetal force on your free body diagram. All right, so a little more about centripetal acceleration and force. So the word centripetal basically means moving towards the center, and it's basically the acceleration that keeps an object moving on a perfectly circular path without falling off that path. It's what keeps planets in orbit and just keeps anything moving in circular motion in general. Centrifugal force is a force that's moving away from the center of motion and represented by an arrow moving in the opposite direction. But it would not actually exist on a free body diagram because it's only an application of inertia resisting a centripetal force. So centripetal force would be on your diagram, while centrifugal force would not be on your diagram. You can feel its effects through inertia, but it wouldn't actually be represented. And then centripetal force is represented by the equation mv squared over r, or the acceleration is represented by v squared over r. And it's important to note here that v is actually going to be using the linear velocity as shown in this image down here. And it's not talking about the rotational velocity, which we will talk about in later dates. All right, so right now we're going to have a very short 5-question quiz, which I will be pulling up, and feel free to join using the link or the QR code. While everyone is joining, I'm also free to answer any questions. I will copy and paste the link in the chat for anyone who cannot view it. Yes, Ben, that is the linear velocity. Alright, I think most people joined, so I will start. Everyone answered, so we'll reveal the answer. All right, so most people got the correct answer, which is that for an object moving in a circle at constant speed, which of the following constantly changes, and this would be velocity. So again, remember that velocity is composed of two parts, magnitude, which equals speed in most cases, and direction. So since the object is moving in a circle, it's constantly changing its direction, so its velocity is changing. Speed is already listed in the question to have a constant speed, so it wouldn't be the correct answer. The mass of an object wouldn't spontaneously change unless something was added to it, and we're talking about a circle, so the radius will also always be the same. All right, let's move on to the next question. All right, I think most people answered, so I'll just go ahead and reveal the answer. All right, so the question was, a Ferris wheel is rotating in a vertical circle. At the lowest point of the circle, the normal force exerted by the seat on the rider is greater than the gravitational force. So this becomes apparent if you draw a free body diagram. So if you're drawing that diagram, normal force would have to point up towards the center of the circle, and gravitational force would be pointing down. And the rider in the Ferris wheel is rotating in a circle. So that means that the rider has to be experiencing centripetal acceleration. That means that it has to have a net force towards the center of the circle. The force that's going upwards towards the center of the circle is the normal force. So that means normal force has to be greater than gravity, which is pointing downwards, for a net positive centripetal acceleration. It's a tricky question, but it gets a little easier if you draw the diagram. That's why you have to know at different positions where the different forces have to be facing and where a force has to face to cause centripetal acceleration. And then I think let's move on to the next question. And just to clarify, I'm pretty sure this question is talking about gravitational force. Is the music okay now, guys? All right, good. All right, everyone answered, so I'm just going to reveal it. All right, so most people got this question right. And the question was, if the radius between two objects is a quarter of the original radius, the new force will be, and the correct answer is 16 times more. So for this problem, you're basically using the equation g times m1 times m2 all over r squared is equal to the gravitational force. And if you substitute in 1/4 r for r in the bottom of the equation, it would equal a 16 times the force. Jacob, gravity and radius have an inverse relationship. So if the radius gets smaller, that means the gravitational force would have to be bigger. Does that make sense? All right. I think most of the questions have been answered in the chat, so I'll move on to the next question. Julia, a couple of these questions might be like ones on the exam. More specifically, many of the questions on the exam typically want you to explain how multiplying different variables or constants affects the overall force. I expect this one to take a bit longer, so I'll give you guys plenty of time. All right, so most people answered, so I'll reveal the answer. So the correct answer was B. And then the question was, a space station is being designed as a ring with a radius of 20 meters. The ring will be rotated to simulate the force of gravity, so the astronauts will not suffer any of the ill effects of microgravity. How fast should the outer edge of the ring be rotating to accurately simulate the force of gravity on Earth? So the correct answer here is B, which is 14 meters per second. So the equation you would be using for this is the centripetal acceleration equation, which equals v squared over r. And you want this number to be as close to the acceleration experienced on Earth, which is 9.8 meters per second squared. So if you substitute in 20 equals r, and then solve the equation for v, you would get v squared divided by 20 equals 9.8. So v squared equals 9.8 times 20. And then taking the square root of that would give you around 14. Here, the masses of the ring and the astronauts doesn't matter, because to affect the astronauts, we're only really trying to affect them, so the acceleration that they experience is similar to the acceleration that Earth Earth gives them, basically. So we only need to use the acceleration formula, which only includes velocity and radius and doesn't include mass. So we'll go to the next question. All right, pretty much everyone answered, so I'll reveal the answer. So about half of you got that centripetal acceleration changes an object's direction, but it doesn't change its speed. So you have to remember here that centripetal acceleration points inwards towards the center of motion. So it's not going to be changing the magnitude of velocity, but it's going to change like the direction of velocity. And you're probably not going to get a question exactly like this on the AP exam, but this is a pretty important concept that you need to know when talking about acceleration and centripetal acceleration. Bria, speed is considered a scalar quantity, and it's only one object, which is like magnitude, and then velocity is speed, which is the magnitude plus direction. All right. Final question. All right, pretty much everyone answered, so let's just reveal the answer. And then the correct answer is C, normal force. And this force is keeping the student in the seat of the roller coaster cart because it's sort of opposing the force of gravity and it's just kind of sticking him there. It's also sort of related to the idea of centrifugal force, which is an application of Newton's third law of motion. And it's basically meaning that he's not going to fall directly down because he's already moving quickly to the side across the roller coaster. So he's kind of falling fast, but falling while moving. That's also why the moon and things that orbit don't fall. They're always constantly being pulled towards whatever object they're orbiting, but their velocity is strong enough that they actually are going to move instead of go towards the object. Normal force is always a contact force, so it will always be opposing the object that is like touching the other object. All right, and that is it for this quiz, but we will be doing a couple of FRQs. Sorry guys, I did mess up my drawing. Normal force is pointing downwards, but this is the force that keeps the students stuck to their seat. I will try to get a whiteboard up for a free body diagram for the last one, or see if someone else can do it. All right, I am having some technical difficulties, so could one of my hosts please try to make the free body diagram while I move on with the slides for now? Okay, Shagun will be making one for me while I move on to the FRQs. So if anyone had questions about the last one, they can refer to the chats for now. All right, sorry guys. So while you're waiting for that answer, try answering this practice MCQ for now. So the question is, a person is swinging a rock at the end of a string as seen from above. If the string breaks at point P, at which lettered path will the rock travel? And if you can't really see the slides, you can click the green button and it should give you a link to the slides. All right, I'm seeing a lot of B's here, and B is the correct answer because B is the only velocity vector that would be tangent to the point P. So tangent basically means that it's touching the circle, but it wouldn't intersect with it at any point if you continued the line on. And it's only going to be a straight line movement because a curve would have to be caused by another force causing some sort of centripetal acceleration, but when the object is let go of, it will just carry on with its movement due to inertia. So B is the correct answer for this MCQ. And then next we're going to, right, so you can see here the centripetal acceleration and that the velocity vector b, which will also be the path of movement, is tangent to that acceleration vector. All right, so next we have a practice FRQ. And then the question is, two identical moons, moon A and moon B, orbit a planet. The mass MO of each moon is significant, but less than the mass MP of the planet. At some point in their orbits, the planet and the two moons are aligned as shown. Draw two free body diagrams of the forces, not the components, acting on moon A and moon B at their locations shown. And then I'll give you a minute or two just to draw that out for yourself, and then I'll show you the answer. All right, so I'll move on to the answer. So your free body diagrams should look something like this, with the forces on moon A acting on the same direction. So the top force would be the force, the gravitational force on moon A by moon B. And the bottom one would be the force on moon A by the planet. And then in moon B, they would be pointing in opposite directions. The force by the planet pointing to the right, and the force by the other moon pointing to the left. And any label really can be used for these forces as long as it's clear that they're not the same gravitational force. And you could say F planet or F moon or FP, and anything like that works, but you just need to make sure to delineate it. The lengths for moon A are the same just because that's the way the artist did them, but we don't really know the lengths between the planet and the moon, so it's a little hard to tell. Honestly, the AP graders are not very picky for this specific problem because you're given a lot of variables. So as long as the arrows are pointing in the correct direction, they will take your answer. Since you aren't given a graph like with dots or boxes, you don't really have to draw the relative length, and you only have to draw the relative length when they specifically ask for it, and that's when they will mark you wrong if you draw something too long or too short. All right, part B. So the first part is justify why the magnitude of the net force exerted on planet A could be greater than the magnitude of the net force exerted on planet B. And then B2 is the opposite. Justify why the magnitude of the net force exerted on planet B could be greater than the magnitude of the net force exerted on planet A. All right, and just type in the chat when you're done. Yes, they meant moon. That was just a typo, ignore that. Yep, they meant moon A and B. Moon A and Moon B have an equal mass. They're completely identical planets. All right, I'm seeing a couple done, so I'll move on with the answer. So for part 1, the forces acting on Moon A could be stronger than Moon B, the net force, because on Moon A, as you can see in the free body diagram, the forces are acted in the same direction, so the net force is calculated through addition. And on Moon B, they're acting in opposite directions, so the net force is calculated through subtraction. And for justifying questions on the AP exam, this is really all you have to give. You don't have to go into any more depth than this. They'll take this as a reasonable explanation. And then for the second part, why the forces on Moon B, the net force could be stronger than the net force on Moon A, we're going to use the force of gravity. So since Moon A is farther than Moon B to the planet, it is possible that the net force of gravity on Moon B is stronger since gravitational force and distance have an inverse relationship. So basically, the force between Moon A and Moon B could be really weak, and the force between the planet and Moon B could be really strong. So it doesn't matter that they are in opposite directions, and Moon B will still have the greater net force. All right, does anyone have any questions for this part? Okay, I'll try to explain why Moon B would have a greater net force. So basically, Moon B is closer to the planet, so it has a smaller radius. So the force between the planet and Moon B will be very strong. And then that means that the force between Moon A and Moon B can be relatively weak. That means because Moon A is so far away, it doesn't really matter that both of the forces are added because the forces on Moon A from the planet and from the other moon are small enough that the force between Moon B and the planet will sort of be stronger anyway. So this part goes into the idea that with a larger radius, forces will be weak. We don't have any values correct, Graham, so we're just justifying why it might be the case in either equation. The first one is the addition-subtraction idea, and then the second one is the distance idea. So we don't know which one is stronger. Both of them could be stronger depending on the actual numbers. All right, now Shagun wants to share her screen just to go back to the roller coaster problem, so I will let her do that.
All right, hopefully this shares soon. Okay, here we go. All right, so just to really quickly just go over that problem before. Honestly, that was not my favorite problem because that's not the best wording. But just to clear everything out, you guys were right. The normal force is pointed downward because if you're upside down, remember the normal force is always perpendicular to you. So therefore, the normal force points downward, and gravity always points downward as well. So in reality, both the normal force and the gravity actually contribute to the centripetal force, and that's what keeps the guy from not falling off. However, I really like this image that I found that I think really explains the concept really well, of how you progress throughout the loop. When you're at the bottom, again, gravity points downwards, and only normal force contributes to your centripetal force because that's the only force that's pointing radially inwards. When you're at the sides, again, gravity is pointing to the left in this, and normal force is towards the right. So it's only normal force that again contributes to your centripetal force. And then if you're at any other point throughout the circle, you're gonna have to use your angle in order to find the your normal force. And gravity will may contribute depending on the angles, but usually there are a lot of times in the FRQs MCQs, you're gonna just be asked like, okay, what's the free body diagram for a guy at the top of the loop, the side of the loop, or the bottom of the loop? Now, remember, centripetal force is very different than centripetal acceleration. A lot of the questions on the AP Physics 1 exam might ask you to find the total magnitude of the acceleration, and just to point that out, is both your tangential acceleration and your centripetal acceleration. And if you do the whole tip to tail method for finding your vector, you'll have to, that's not the best diagram of vector, but for example, if I have my acceleration going that way and my centripetal acceleration going that way, then my total magnitude of acceleration will be going that way. So that's just the types of MCQs you can find. It's usually about these forces, these free body diagrams, or the centripetal acceleration. So yeah, I just hope that clears things out. You guys were right. That's not the best wording of the questions. You don't have to worry about that much, but you will just have to be cautious on what the normal force is and what the gravity is. But yeah, hope that helped. Thank you, Juliana. Back to you.
All right, I hope that Shagun's message helped you guys out for that problem. Sorry for the confusion earlier. And then we will move on to the next part of this practice, FRQ. So if you can't see this, it says derive expressions for both of the following quantities. Express your answers in terms of MO, MP, RA, RB, and physical constants as appropriate. So we want the equations for the net force FA exerted on Moon A and the net force FB exerted on Moon B. MO is the mass of the moon and MP is mass of the planet. Don't forget to type when you're done in the chat. All right, I'm seeing a couple of done, so I'll move on with the answer. So the answers are down below. You can see that the only forces that are acting on Moon A and Moon B are gravitational forces. So we would be using the equation G m1 m2 over r squared. And what you basically have to do for each force is just make sure that you're plugging in the correct constants. So for example, the first force for net force for the Moon A would use MO MP because we need the mass of Moon A, which is MO, and then the mass of the planet, which is MP, and their distance is RA. For Moon B, we have negative signs because the force towards between the moon and the planet is considered positive, but the force between Moon A and Moon B is considered negative because it's pulling in the opposite direction. And we're assuming that since the mass of the planet is a lot larger than the masses of the moon, that the mass of the planet will have the stronger gravitational effect. So we're just going to make that one positive. Yes, Chivo, you will still get the points if you don't simplify it, as long as you put everything in the constants they want you to. All right. Does anyone have any other questions before I move on to the next part? Yeah, sigma just means net force, so it means you're like adding them. It is necessary in this case because it just symbolizes that this is the net force, but you can write it out. You don't have to use the symbol. Oh, M0 is squared for FA because you're going to do mass 1 times mass 2. And the planets have equivalent masses of M0. So that'd be M0 times M0 or M0 squared. Factoring is not necessary, and you can write FNet. It's just your personal preference or whatever's faster in the exam. All right, I think we're all set for questions, so we'll move on to the last part of this FRQ. So this is part D, and it's could the expression in part C support your reasoning in part B1? And this was the part about Moon A having a stronger net force than Moon B, and then explain your reasoning. And then part 2, which is could the expressions in part C support your reasoning in part B2, which was that Moon B would have the stronger net force. This is the last part then. And then as always, just type in the chat when you guys are done. All right, I'm seeing a lot of done, so we'll move on. So this is just an easy explanation for the previous part. So for D1, you could say the two components of net force and force A are added while they are subtracted in force B. So they have a greater effect in force A and cancel in force B. And for part D2, you could say that gravity and distance have an inverse relationship and just compare how if RA is very large, then the forces for Moon A will be very small. And if RB is pretty small, then the forces on Moon B will be comparatively larger. So in these questions, you really have to depend. Yes, it is yes for both. For these questions, you really have to depend on looking at your answers to the past parts and sort of using that to build your answer. And also you have to maintain consistency in your answer. So if you get something wrong in the first part, you can actually get points later on as long as you are consistent with your answer. If you somehow change your answer between both, you won't get any points. All right, so we have one more FRQ for this unit. Does anyone have any questions before we move on? If you have time and you verify, I do recommend you go back to the past. But if you don't have any time to rework your whole like AP FRQ answer, then I recommend just leaving it so you grab those points for consistency. It really does depend on how much time you have. Does anyone else have any questions before we move on? You should probably do some studying for your calc final. All right, Jessica, which forces did you want explained? Okay, FA on Moon A. Oops. Sorry, guys. I will just move backwards to get it a little bigger for myself. All right, there we go. So the two forces on Moon A are the forces on Moon A by the planet and the force on Moon A by Moon B. And both of these are gravitational forces. So you would use G m1 m2 over r squared. So for the first component, A and the planet, the two masses you would use are MO and MP because that's the mass of the moon and the mass of the planet. And for the radius, you would just use RA because you can see in the picture that's the distance between Moon A and the planet. And then for Moon A and Moon B, you would use MO squared because that would be MO times MO, and both moons would have the same mass. And then for the distance, you would use RA minus RB squared because the distance between Moon A and Moon B is RA minus RB. All right, I hope that helped. All right, does anyone have any other questions for this unit before we move on to the next FRQ? Yes, I do recommend if you don't know how to calculate with the variables, you just make a reasonable random number up. Or you can just plug in a random number, but I also don't recommend if you're going to try to do the plug-in method, not to choose a number like 0 or 1, because that can give you false positives or false negatives, because a lot of those numbers will cancel out in a variety of equations. So choose something like 2 or 3 instead. All right, I think we're all set to move on to the next FRQ. All right, so this is part A. And then the question is, a spacecraft of mass m is in a clockwise circular orbit of radius r around Earth, as shown in the figure above. Mass of the Earth is me, and then in the figure below, or just on your paper, draw and label the forces on the spacecraft. Each force must be represented by a distinct arrow starting on and pointing away from the spacecraft. And then just type when you're done. Okay, I'm seeing a lot of dunce, so we'll move on. And then this is the only force that would be acting on the spacecraft, which is the force of gravity. And it would be pointing towards the center of the Earth. All right, part 2. What about V? If you're talking about velocity, velocity isn't considered really a force. We're just talking about forces. The vector of velocity would exist, but they're only asking about forces. All right, part B1. Derive an equation for the orbital period t of the spacecraft in terms of lowercase m, capital ME, r, and physical constants as appropriate. We don't put centripetal force on space free body diagrams because it's not an actual force caused by an object. It's just a net force. So it can be like tension force, gravitational force. It's only a number and it isn't an actual force. All right, type when you're done finding an equation for the period, or just type if you need any help or hints. Okay, I'm seeing some hint requests. Put up a couple of hints. Emily, we would not be using omega right now because we're talking about linear velocity and not angular velocity. Although I suppose if you wanted to, you could solve this problem using angular velocity. All right, I'm seeing a couple of dones. So does anyone need more time? Okay, I think we'll move on for now. Okay, so before getting into the math of this, I just wanted to put down a couple of my assumptions and like how I went about solving this problem. Up top is just m equals Earth mass, m equals mass of satellite, which is the variables that I used. And so the first thing I used was that speed equals distance divided by time. So in this problem, speed is the magnitude of the linear velocity, and the distance traveled in one orbital period of time. This is the circumference of the circle, which is 2r pi, or 2 pi r. And then the time taken is one orbital period, or t. So substituting that back in, velocity equals 2 pi rt. And then also the only force acting on this object is Fg, or the gravitational force. And this force also provides the net acceleration necessary for circular motion. So Fg equals the acceleration force, which equals the centripetal force. So moving on to the actual math, at the bottom left, you're going to see what I'm solving for. T equals 2 pi r over v. So v equals 2 pi r over t. And then starting at the top left, I made f of g, which is on the left, equal to f of centripetal acceleration in force. So the next step is I multiply both sides by r squared. And then I divided both sides by mr to get v squared equals g times mass of Earth divided by r. And then after that, I moved into the earlier equation that v equals 2 pi r over t. So earlier, I derived something for v squared. And what I could do is I could take the square root of that equation. But personally, I prefer to take the square root at the end, as I think it makes things less complicated. It's really up to you how you do it. F equals ma, so F equals mv squared over r. We're not setting the force of gravity equal to acceleration. It just divides out. All right, moving back, v equals 2 pi r over t. So v squared equals 4 pi squared r squared all over t squared. Substituting in the earlier value for v squared, which was g times mass of Earth over r, I'm setting that equivalent on the third equation in the second column. And then after that, I'm doing some algebraic manipulation. So I'm multiplying each side by r and dividing by gme. And then I just multiply t squared out to get t squared equals 4 pi squared r cubed all over gme. And then to get t, I would just take the square root of that. And then the final two equations on the bottom are what you would submit to the AP graders. And the second equation from the bottom would check out, and they wouldn't require you to simplify because the t is already set. The mv squared over r comes from the formula for centripetal force, which is equal to gravitational force. Does anyone have any questions about how I derived this? Yes, we are saying gravitational force equals centripetal force. Okay, so I just realized that this equation is actually on the AP Physics 1 formula sheet. It's just kind of hidden. So on the formula sheet, I'm looking at the second page, right under like what it says, what all the constants represent. I mean, the letters. And then it's going to be the second equation down on this column in mechanics. And this says T equals 2 pi divided by omega. And omega is going to be the angular velocity. So we can convert from angular velocity to, what do you call it, to linear velocity by multiplying or dividing by r. Wait, let me just work it out. Sorry, guys. Times r. All right, thanks, Carmen. Yep, omega times r equals v. So if you multiplied the numerator and the denominator by r, you would get 2 pi r over v is equal to 2 pi over omega. So that's basically how I got that equation. Yes, correct, Carmen. Yes, this is technically Kepler's third law, but you're not required to know it. You can use this math to substitute it out. It's a difficult question. This is where you get the bulk of your points, I think. Bank curves are basically curves that are raised so that the centripetal force comes from gravity and friction, but I've literally never seen a problem using them, and they're very, very difficult to do. Yes, linear and tangential velocity are the same for circular motion. All right, if anyone has having any problems figuring out why period equals 2 pi r over v, just check out Ari's comment because it does a pretty good job explaining it, or I can try to explain it again if anyone is still really confused. Then you can use angular velocity. I'm just using linear velocity because it's what we have covered right now, but you are perfectly okay with using angular velocity. Yes, you'd still get points, Sherry, because it's a mathematically equivalent expression. All right, I think everyone is set with this part, so we'll move on to B2. So for recap, since this problem took a bit of time, B2 was a second spacecraft of mass 2m is placed in a circular orbit with the same radius. Is the orbital period of the second spacecraft greater than, less than, or equal to the orbit period of the first? And then just type when you're done with your answer and your explanation. Okay, I'm seeing a couple done, so I'll move on. And then you can see here that the orbital periods of both satellites are equal because the equation for period is only dependent on the radius and the mass of Earth. So changing the mass of the satellite doesn't affect the period. All right, and moving on to part C. So the first spacecraft is moved into a new circular orbit with a greater radius. Is the speed of the spacecraft greater than, less than, or equal to the original speed? And don't worry, guys, this is the last problem right before our break and we switch over to energy. Okay, most people are saying they're done, so I'll move on. So the spacecraft in the new orbit is slower because radius has an inverse relationship with the force of gravity, which has a direct relationship with velocity as it causes centripetal acceleration, which is v squared over r. So a larger radius means weaker force of gravity and a slower speed. Also, in this problem, the AP graders will take it if you just say, look at this part of the equation I derived in B1, and that's why it has a slower speed. You don't have to explain it in too many words. Yes, there's multiple ways to explain this, as long as you can show that speed and radius have an inverse relationship. The AP graders will take pretty much any answer. All right. Are there any Q&As about Unit 3 before we take our break? All right, I'm not seeing any Q&As, so we will be taking our 5-minute break right now, and then we will be coming back for energy. Oh, I see a couple questions, but I will answer them in the chat.
All right, so now we are going to be starting with the unit 4 energy. Next slide, please. Energy basics. So energy is the ability or capacity to do work. Kinetic energy is displayed through movement, and the equation for this is going to be 1/2 times mv squared. Potential energy is displayed via position, elastic, and gravitational. So the equation for this is going to be 1/2 kx squared. And the gravitational potential energy is going to be mgh. There's also mechanical, non-mechanical energy, which includes thermal and chemical energy, and there are no direct formulas for this. And then systems are another thing we're going to go over, and it is energy in a closed system is a constant. So mechanical energy equals kinetic plus potential. In a closed system, no outside forces act on the object in the system. Next slide, please. So here's a quick practice question to start off. A planet orbits a star X. Which of the following systems can be considered a closed system? So I'll be making a poll right now real quick, and you guys can answer on there. All right, the poll should be up. All right, I'm seeing a lot of answers coming up. All right, so I'm seeing a lot of people voting for B, and B is the correct answer, system with star X in the planet, because energy passes across the planet system, but not mass. So it makes it a closed system because you don't pass mass through the system, only energy. Next slide, please. Work and mechanical energy. So work can be positive, negative, or 0. So the equation is going to be the work equals FD cosine theta. So W equals work, and then F will be your force. So D equals the distance over which the force is applied between the force and, or the angle is going to be the force. Sorry, angle is going to be between the force and the displacement. So positive work is done when the force and displacement are in the same direction. Negative work is going to be done when they're going to be in opposite direction. So 0 work is going to be done when there's no net displacement or when the force and the displacement are perpendicular. So the area under the curve of a force versus distance graph is going to be your work done. All right, next slide, please. Kinetic energy. So kinetic energy equals to 1/2 mv squared. M is going to be mass and v is going to be your velocity. So for kinetic energy, it is part of the work energy theorem. Energy an object has when it is moving. So velocity has a much more significant effect on kinetic energy than its mass. So some examples are like ramps, roller coasters, and just anything with like a slope. And in diagrams, the lowest point in height has the largest kinetic energy. Next slide, please. So the gravitational potential energy, I'm going to be handing this over to Zeke, our next presenter for the gravitational potential energy. So the gravitational potential energy is going to be mgy, so m is going to be mass, g is going to be gravity, and y is going to be the coordinate value in y dimension. So the potential energy an object has due to its position within the gravitational field of a massive object like a planet. So the higher the object is above the surface of the planet, the more gravitational potential energy the object will possess. So we will wait a minute. And we are going to be moving on to the next slide. So the spring potential energy. So the equation for spring potential energy is going to be 1/2 kx squared. So k is going to be your spring constant, x is going to be your displacement, potential energy an object has when a force has been used to deform an elastic object. So energy is stored until the force is removed, and an object will spring back to its original shape. So K is going to be your spring constant, which is the measure of a spring's stiffness, and springs have a restoring force to bring them back to equilibrium. Kinetic energy is going to be greatest at your equilibrium. So you can look at the graphs to visualize the compressions of the spring potential energy. Next slide, please. So the conservation of energy is going to be mechanical energy equals kinetic energy plus your potential energy. So U of S is going to be 1/2 kx squared UG equals mg y. And I'll now be handing it over to Zeke, which will continue the conservation of energy.
Okay, I'm not quite sure where we left off, so I'm just going to start from the beginning. So the big thing with conservation of energy is your mechanical energy is going to equal your kinetic energy plus your potential energy. Your potential energy is going to include spring potential energy and gravitational potential energy. And we see our equations right below that. So we have U sub S, which is our spring potential energy, and that equals our spring constant multiplied by our displacement squared over 2. We have our gravitational potential energy, which we see as U sub G, and that equals mass times gravity and the y dimension. And then we have our kinetic energy, which is 1/2 the mass multiplied by velocity squared. If no outside forces are acting on the system, the total mechanical energy will be conserved, and we can see this as mechanical energy initial equals mechanical energy final. And if we write that out fully, we can write that out as gravitational potential energy initial plus spring potential energy initial plus kinetic energy initial equals gravitational potential energy final, spring potential energy final, and kinetic energy final. This graph is also really important. I've seen multiple choice questions on the AP test ask about this on free response and multiple choice. Just know that when you add your potential energy and your kinetic energy, you will get a straight horizontal line that represents your mechanical energy when energy is conserved. Okay, we can move on real quick. So now we have the work energy theorem. This is another really, really important thing out of energy. You definitely need to know your energies, but it's going to be most important that you fully understand the conservation of energy and the work energy theorem. So the work energy theorem is basically just going to state that the net work done is going to equal the kinetic energy final minus kinetic energy initial. And you can relate this to the definition of work. And remember, work is going to be the force multiplied by the distance. And so that means that our kinetic energy final minus our kinetic energy initial is going to equal the force multiplied by distance. And then we can use this relationship to find the relationships with work, speed, mass, and distance. And we can move, okay, here we go. So now we're on power. I don't see this too much, but it's still important that you guys know what power is and the different equations that you can use to find power. So power is going to be the rate at which energy is transferred into or out of a system or converted within a system. And there's quite a few equations that we can use to find power. 3 of the most common ones that I've seen are going to be power equals force times distance, cosine theta divided by your change in time. Power can also equal the change in energy over the change in time. And then another common equation is power is going to equal the force multiplied by velocity multiplied by cosine theta. And we can move on. So some main takeaways are going to be, let me see real quick, will you ever use sine instead of cosine? It depends on really the problem. Most often, no, though. Okay, so main takeaways, right? The work energy theorem is important because it's going to connect force and energy. So force is going to control acceleration, and it's always related to movement. Like if you have a force pushing on an object, it's going to move. It's causing it to accelerate. Force is not necessarily conserved, and force relates to work because work is force times distance, cosine theta. And then energy is going to be related to movement or position. So remember, we have spring potential, gravitational potential, and kinetic energy. And energy is going to be conserved in a closed system. And that, once again, relates to the conservation of energy. Energy also relates to power, which is energy per second. And your all-in-one useful equation is going to be force multiplied by distance equals the change in kinetic energy. Is it just change in KE or all energy? It can depend, right? Because when energy is conserved in a system, whenever you're changing your kinetic energy, you're also changing your gravitational potential energy or your spring potential energy. So you could use those. You would just have to change it from, I think, instead of final minus initial, you'd have to do initial minus final. And I can go ahead and do this practice question also. Okay. So our question says, consider the roller coaster below. The cart travels on the roller coaster track and has different kinetic energies at points labeled A through E. At which point does the cart have the greatest kinetic energy? Assume friction is negligible and the system contains the roller coaster, track, the cart, and the earth. Okay, so we have our diagram here, and the green dots are labeled as a point. So I'm going to give you guys a couple of seconds to answer this, and then just put your answers in the chat. Okay, I see a lot of C's. Okay, so a lot of you guys have answered this. Let's just go right in. Your answer is going to be C. That is because it is the lowest point on the lowest height, right? because when we're starting at the top of our track, the height is the greatest. That means that gravitational potential energy is going to be the greatest. And we know that our energy is conserved because our system includes the roller coaster track, the Earth, the roller coaster cart. And we also know that friction is negligible. So that means that we have no force due to friction acting on this, right? And since our energy is conserved, then you have an inverse relationship between gravitational potential energy and kinetic energy. So when your gravitational potential energy is the greatest, your kinetic energy will be the smallest, right? So when our gravitational potential energy is the smallest, that means that our kinetic energy will be the greatest. And that is why our answer is point C. And we can move, well, yeah, we'll just transition on this slide, but it just has more explanations of this problem. Yeah, we see the answer is C. We know that the mechanical energy is conserved because the question tells us our system includes the roller coaster track, cart, and the Earth. And we also know that we have negligible friction, as I stated. And then we can click again. And because of this, we can use the conservation of energy and relate kinetic energy to gravitational potential energy, which is also what we did. And then we'll click one more time. And we know that our gravitational potential energy equals the mass times gravity times height. So as our height decreases, our kinetic energy will increase because mechanical energy initial equals mechanical energy final. And gravitational potential energy initial plus kinetic energy initial will equal gravitational potential energy final plus kinetic energy final. So point C has the lowest height, so KE will be the greatest. And let's go to our next slide. Okay, so now we have an FRQ that we're going to start doing. I'm going to read it out to you guys, and then the next slide will have the question. I'll let you guys work each part of the question out for a couple of minutes until you guys are done. And then I have video explanations that I will have going over each part. So let's just start off by reading the question. So a physics class is asked to design a low friction slide that will launch a block horizontally from the top of a lab table. Teams 1 and 2 assemble the slides shown above and use identical blocks 1 and 2 respectively. Both slides start at the same height d above the tabletop. However, Team 2's table is lower than Team 1's table. To compensate for the lower table, Team 2 constructs the right end of the slide to rise above the tabletop so that the block leaves the slide horizontally at the same height h above the floor as does Team 1's block, and then see the figure above. And then let's go to our next. Oh yeah, so this is just part A. It says both blocks are released from rest at the top of their respective slides. Do block 1 and 2 land the same distance from their respective tables, yes or no, and justify your answer. So I'm going to give you guys a couple of minutes to work this out. Just type in the chat when you guys are done, and then we will go on to our explanation for this part. Okay, we're gonna wait for a couple more of you guys to finish and just keep on typing in the chat when you're done. Okay, and we will now move on to the next slide that has the video explaining this answer. Hi everyone, Zeke here with Fiveable to go over part A of question 4. So I'm going to read it again real quick to you guys. The physics class is asked to design a low friction slide that will launch a block horizontally from the top of a lab table. Teams 1 and 2 assemble the slides shown above and use identical blocks 1 and 2 respectively. Both slides start at the same height d above the tabletop, however Team 2's table is lower than Team 1's table. To compensate for the lower table, Team 2 constructs the right end of the slide to rise above the tabletop so that the block leaves the slide horizontally at the same height h above the floor as does Team 1's block, and then see the figure above. Both blocks are released from rest at the top of their respective slides. Do block 1 and block 2 land the same distance from their respective slides, yes or no, and justify your answer. So right now I'm thinking about distance, and I see, I want to see if they're going to land the same distance from their tables, and I also know that I'm given a height and a distance, right, for the slides. And I also know the slides have low friction, so we're going to assume that friction is negligible, okay? So let's look right here, right? This is going to be our change in our H, and that's going to be related to our gravitational potential energy. And this is going to be our total change of our H, which is going to be related to our gravitational potential energy. So since I lost more gravitational potential energy in block 1 slide, that means that my kinetic energy at launch is going to be greater. And that means that my kinetic energy at launch here is going to be less because it's not at the lowest point of the slide. Okay, so now let's go to our answer. Are they going to land the same distance? Well, we now know that the kinetic energy is going to be greater at launch for table 1, but table 2 is going to have a smaller kinetic energy, right? We also know that the time to reach the ground is still going to be the same for both blocks, right? Because let's think back to projectile motion. The time is going to be related to our h at the very end, right here. And that's just going to be force due to acceleration of gravity, right? So now let's go back to answer the question. Let's see. So are they going to land the same distance? No, right? And we can earn 3 points on this question. One is going to be for attempting to use the conservation of energy for both blocks, which is what we did, right? I looked over here and I found that my kinetic energy was going to be greater and it's going to be lesser right here, right? So let's think about that. Conservation of energy. Slide. Team 1 slide. Will launch block 1 with a greater velocity because velocity is related to kinetic energy than team 2's block. Because I know that as mgh decreases, my kinetic energy will increase. And we also got another point for already saying that our launch velocities are going to be different, right? Now our other point is going to be for stating or implying that the time to reach the ground is going to be the same for both blocks. And that's because, let's just write that out. Time to reach the ground will be the same for both the blocks. Same for both blocks. Because H is related to the force due to gravity, right? So when we're going down, the only thing that's actually acting on that is the force due to gravity. And that's a big thing with projectile motion, right? Is separating, is separating your horizontal from your vertical, because the only thing that relates them together is the time, right? So if we still have a greater velocity on table 1, that means that it's going to launch horizontally farther. Whereas this one is going to launch horizontally smaller. But your horizontal motion has nothing to do with your vertical motion, so that's why they want you to state that there. So just that, gosh dang it, is 3 points. Okay, I hope that helps you guys. Now we're gonna go to the next slide and look at the scoring guidelines. So this can help answer some of your guys' questions about asking other ways that you can justify it. I know, Sydney, it's something really random. I'm not exactly sure why it asked for that, but they do. Yeah, just brain dump to try and get everything you can, okay? Okay, so like I said in the video, the correct answer is no, and it is important. Remember, they're going to give you guys partial credit on here if you're still using whatever answer you got and using it correctly in your next steps. So, yep, the note is if the wrong answer is selected, partial credit can be earned for the justification. So if you said yes, and you still justified why that was correct, then you can still get the 2 points, I think, on this is what it would be. But you get 1 point for attempting to use the conservation of energy to compare the two blocks, which is what I did, right? Your gravitational potential energy and your kinetic energy in this case. If you get the right answer and explained it wrong, would that equal partial? It can be tricky with that, Ruthie. Sometimes, actually, if you put the right answer and you give the wrong explanation, you get 0 points. So it can be tricky, but it's better to try and explain them. And because if you just put like no on here, you'd get 0 points for that. Like you have to have the explanations to get any points. Is it okay if we said block 2 loses some kinetic energy when it moves up the ramp, so it travels less horizontal distance? I mean, yeah, because it's saying that that should work. I mean, they're going to be understanding with what you guys are saying. You just need to think about, like, let's go back to the points that you're going to get for this, right? So your next point is for explicitly or implicitly indicating that the launch velocities are different. So you can use any explanation like, oh, it lost some kinetic energy and, the height increased, but you still need to be able to determine that the launch velocities are going to be different. And then another point is for stating or implying that the time to reach the ground is the same for both blocks. Once again, this is kind of a random point, I think, but just think about it. I mean, it is somewhat projectile motion, which is kind of what is going on here, because the vertical and horizontal components are going to be different. And for an example, if you guys didn't really like my video explanations, the amount of potential energy converted to kinetic energy is different for the two blocks. That's what I was saying in the video. The potential energy is proportional to the change in height, which is smaller for block 2. Therefore, at the edge of the table, block 1 will have more kinetic energy than block 2, and hence the larger speed. The launches are both horizontal and from the same height, so the blocks will spend the same amount of time in the air. Because d equals vt, the distances will be different for the two blocks as the speeds are different. So now we can move on to the next portion. Wait, okay, I did do that. Okay, so yeah, let's go to, I'm gonna read this to you guys real quick, and then I'll give you guys some time to try and solve this, and then I also have video explanations for both parts. So part B says both blocks are released from their respective. Let me read the top of this. Sorry guys, it's so small. In another experiment, teams 1 and 2 use tables and low friction slides with the same height. However, the two slides have different shapes as shown below. And then B says both blocks are released from their respective slides at the same time. And then BI says which block, if either, lands farther from its respective table. Block 1, block 2, or the two blocks land the same distance from their respective tables. And then for BI, you need to be able to briefly explain your reasoning without manipulating equations. And then for B part 2, it says which block, if either, hits the floor first. Block 1, block 2, or the two blocks will hit the floor at the same time. And justify your answer without manipulating equations. Okay, I'm gonna give you guys some time. Type in the chat when you guys are done. And then when most of you guys say that you're done, we will move on to the explanations. Chloe, the shape of the ramp is not going to change like the total distance of it, if that's what you're trying to ask. We're more worried about in this problem the starting height and the end height than the shape of the slide. I'm gonna wait for some more of you guys to answer. I would like to see some more dones in the chat, or at least know that you guys have tried to solve this problem. Okay, I think that the majority of us are finished, so let's go to the next slide and watch the explanation for B part I. Okay, now let's do Okay, now let's do part BI real quick, right? It says in another experiment, teams 1 and 2 use tables and low friction slides with the same height. However, the two slides have different shapes as shown below. Both blocks are released from rest at the top of their respective slides at the same time. Which block, if either, lands farther from its respective table? Block 1, Block 2, or the two blocks land the same distance from their respective tables? Briefly explain your reasoning without manipulating equations. Okay. So let's think about this again, right? We know that, similar to the other question, our H is going to be right here, and that's going to be related to our gravitational potential energy. But this time the change is the same. And our gravitational potential energy is going to be related to our kinetic energy. And if you look here, they both end at the same height, which means that your kinetic energy of, let's just write it down, KE team 1 equals KE team 2. Because the change in gravitational potential energy is the same, they're both being launched from the same height. So we already determined that the two blocks land the same distance from their respective tables, because remember, your kinetic energy is going to be related to your launch velocity. So let's put that also. Launch velocity will be the same. Right? And what else can we say here? I mean, you just have to make sure that you're explaining without manipulating equations, and really we did that. Remember, it's briefly explained. You guys don't have to put an elaborate paragraph. We might want to add, though, that the change in gravitational potential energy, is the same for both slides. So the kinetic energy of team 1 and team 2's blocks will be the same. Therefore, they will land the same distance. And that right there was 2 points. Okay, hope that helped, and let's move on. Okay, we are now going to move on to the next slide that does an explanation for Part B, Part B, Part 2. Okay, now let's do I believe. Yep. So we're going to watch the explanation for that, and then we'll look at the scoring guidelines when we're done. Finish off our free response real quick with Part B, Part 2. It says which block, if either hits the floor first, Block 1, Block 2, or the two blocks hit the floor at the same time. Briefly explain your reasoning without manipulating equations. Okay. Let's think about this for a second. We're still dealing with the conservation of energy, gravitational potential energy, and kinetic energy. Now it wants to know which block would hit the floor first, right? Well, what I can think about is which block is going to reach its maximum average velocity first, right? We both know that they're still going to end at the same height, which means that their kinetic energy would be the same. But now we need to figure out which would reach it first, right? And that's going to be block 1 because our slide is steeper, right? Whereas block 2, we're starting out here and kind of going down slower and slower. Whereas block 2 gets straight to the point and just increases at a faster speed. And because of that, block 1 is going to hit the floor first, and that's going to be because block 1 will reach its maximum speed in less time, because our gravitational potential energy is increasing faster. Okay. And we also need to, put our explanation for that. So that can be our explanation, right? Because gravitational potential energy is decreasing at a faster rate, and therefore kinetic energy increases at a faster rate. Okay. And now we need to kind of relate that back, right? So if, let's think about how to word this, right? Block 1 reaches its maximum speed faster, or maximum speed in less time. In less time than block 2. Therefore, block 1 will launch off of the table before block 2 does. And therefore reach the floor faster. That was kind of a long one. That was another 2 points. And I hope I did a good job at explaining for you guys and helping you guys feel more confident about free response, especially in relation to the conservation of energy. Okay, we're now going to move on to the scoring guidelines for Part B 1 and 2. And before we start going over that, this just demonstrates how important energy is on the AP exam, right? That was basically an entire FRQ just over the conservation of energy. So you guys really need to make sure that you completely understand conservation of energy, work energy theorem, all parts of energy, because that was 7 points right there. So for Part BI, the correct answer was the 2 blocks land the same distance from their respective tables, and you would earn 1 point for indicating that the change in potential energy from release to launch is the same for the 2 cases, and another point for an indication, explicit or implicit, that the launch velocities are the same, right? And for Part 2, which block of either hits the floor first, the correct answer is going to be block 1. This FRQ was almost designed to trick you, because in Part 1, you guys had to state that they would hit the ground at the same time, right? The time was the same, but now they're not. And Jacob, it depends. This FRQ was 7 points in total. That's how much your short FRQs will be worth. And then your long FRQs, I believe, are worth 12 points. And your suggested time is going to be different for both because of that. But back on to part 2. So you would earn 1 point for indicating that the average speed or velocity on the slide is higher for team 1, or that block 1 reaches its maximum speed in less time, right? And that's because our gravitational potential energy is changing at a faster rate than it is in team 2's slide, right? And you get another point for a valid explanation of why the average speed or velocity is higher for team 1, or why block 1 reaches its maximum speed in less time. An example explanation you could have for that would be because the ramp on table 1 is initially steeper, block 1 is a higher average speed while it's on the ramp, so it launches off the table before block 2. Okay. And yes, the time is 13 for shorter FRQs and 25 for longer. And we will move on to our next slide. And we have a quiz. Give us 1 second to try and get this to work. Okay, give me 2 seconds and I'm going to drop the quiz link in the chat. Let's start. Looks like quite a few of you guys are already joining. Can y'all hear the music? Okay, 58 of you guys have joined, so let's try and get most of you guys to join. Okay. And this quiz is going to be a little bit different than usual because I can't actually put it on my screen, so I will just be explaining how I am now, and we'll just do it like that. Okay, there's 64 of you guys. I'm going to go ahead and start it, and you guys can still join after if you guys are taking a few minutes to get on there. Okay, it looks like one of my fellow Cram hosts is going to try and share her screen so that you guys can still see the questions on the screen. So I'm going to wait to try and do that, and then if we can get that to work, I will start it. And thank you, Ari. Okay, so we have Julia's screen on here, and I'll be going along with it. So let's go ahead and start the quiz. Sorry guys, I was on mute, but Anastasia is going to the first question with you guys. Okay, I'm going to check how many of you guys have answered. It looks like quite a few, so we're going to go ahead and reveal the answer now. And just in case you guys weren't able to read it for any reason, the question states an open system can exchange blank with its surroundings. Let's go ahead and reveal the answer, and then Anastasia will give you guys an explanation.
All right, so the answer to this is going to be both. You can think of this as a stovetop example with an open system. With an open system, you are going to have like heat and water vapor in the stovetop example. So you can think of it as that, where in an open system, it's both energy and it's also going to be mass exchanged.
Okay, I'm going to go ahead and go to the next question, and I will give you guys some more time to answer that. It asks, at what point in the motion of a stone thrown directly upwards does it have minimum kinetic energy? A, halfway up to the peak, B, moment before hitting the ground, C, the peak height, or D, the initial moments following the throw. Okay, it looks like almost all of you have answered, so let's go ahead and reveal the answer. And it is C, the peak height. So let's think about this. In what point does it have the minimum kinetic energy? Remember, our kinetic energy is going to be greatest at our lowest height. That was on the slide. That was a part of the FRQs we just did. That is just something that you are going to have to ram into your brain, because that is part of the conservation of energy. And remember, energy is going to be 20 to 28% of your AP exam. And in reality, it's going to lean closer toward that 28%. Okay, is this our highest? Oh, sorry, I think that's something else. Okay, let's move on to the next question. It says, when a spring is fully compressed or stretched, it has A, its maximum kinetic energy, B, no change in energy, C, it has maximum potential energy, or D, it has 0 joules of net energy. And when we reveal this answer, Anastasia will be going over the explanation with you guys. All right, we're going to go ahead and reveal the answer, and then once again, Anastasia is going to be going over the explanation with you guys.
So when a spring is fully compressed or stretched, we can, as we're looking at a problem with anything that has to do with a spring, it's going to have to do with the potential energy. So with the potential energy, we have two answer choices left, which is either maximum kinetic energy or maximum potential energy. So obviously it's going to be maximum potential energy because when it is compressed or when it is stretched, it is gaining potential energy. So the answer is C.
Okay, thank you, Anastasia. And now we're going to move on to question 4. So question 4 says, a student plots a graph modeling the force applied on a toy car, and you guys are going to assume that it's a frictionless surface versus the horizontal displacement traveled. How can the work done on the car be determined graphically? You could A, calculate the area under the curve of the force, B, the displacement graph and take the square root. C, you can calculate the slope of the force versus displacement graph. B, you could calculate the area under the curve of the force versus displacement graph. Or D, you could calculate the slope of the force versus displacement graph and multiply it by 2. LOL, there are 6 questions in this quiz. Okay, I'm going to wait for a couple more of you guys to go ahead and answer this. Okay, let's go ahead and reveal our answer. So the answer is B, calculate the area under the curve of the force versus displacement graph. And that's because we are trying to determine the work that's done, and work is force multiplied by displacement. So what we can do is we can graph the force versus displacement in a graph, and the area underneath the curve would equal the work that's done. That's the same thing with velocity and a velocity and time graph and the displacement done for anything that's moving. And this is just a really big topic on the exam, and you'll also see it in rotational motion. So that's another thing that you guys just really need to get down. Okay, we're going to do question 5, and then Anastasia will be back to give you guys an explanation for it. Okay, so number 5 says power is defined as the A, rate at which work is done, B, the force multiplied by displacement, C, the ability to conduct electricity only, and D, the ability to accelerate. Okay, it looks like most of us have answered, so I'm going to reveal the answer, and it looks like it was A, and Anastasia is going to come on and explain this to you guys.
So the answer is going to be A because as the question states, it is power is defined as what? So power is going to be work over time. That's an important thing to remember. It's always going to be work over time. So since it's over time, that means it's going to be a rate. So as you can see, it's going to be A, rate at which work is done, and all the rest of them you can easily eliminate since it has nothing to do with work.
Okay, I'm going to come on here and we're going to do one last question. And let's go ahead and get with it. It says, what is the equation to find power? You have A, power equals the change in energy over time. B, power equals force multiplied by velocity. C, all of the above. And D, power equals the work divided by time. Okay, it looks like most of us have answered, so I'm going to go ahead and reveal my answer. It is C, all of the above. This can be important if you are asked to calculate power. It's going to be more of an FRQ question, if anything. It can be really helpful, though, to know all of the different ways that you can calculate it, because you can also, if given power, you can use it to find other variables, right? Now you can use it to find velocity, force, change in energy, time, work. You can use it to find a lot of different things. And that's why power is a really good thing to have and to know all of the equations for, because also if it's asking for power and you're only given force and velocity, that's going to be really important that you know that question or that equation for it. So that was the end of our quiz, and now we're going to go back to our slideshow and finish off for the night. So now we're going to do a Q&A. So type any questions you have in the chat, and we will go ahead and start answering some questions that you guys have already posted. If you guys are confused about anything, type it in the chat. Can we do more practice problems involving work, please? We can do more practice problems involving work. We don't have anything for that right now, but we can make sure to do that on night 5, because night 5 is going to be our wrap-up night. So we're really going to be doing what you guys want to do. And we're going to be doing FRQs and just multiple choice questions all night long to help you guys feel prepared for that. So that's another thing, is if you guys after tonight are still like, man, I really would like some more time with energy or like work or spring potential energy and its relation to kinetic energy, type it in the chat so we can make sure that we can go over it on night 5. And yes, scalar is just going to be, yeah, it looks like you guys have already done that. But yeah, vector has magnitude and direction, but scalar is only direction. Okay, let's see. How do you determine whether an energy graph is curved or linear? If you're talking about like, it's really going to depend on if you're the rate at which your energy is changing, because this is going to be really involving conservation of energy. I don't know if you guys remember, but in the slides, there was a graph where it had the relation of the total mechanical energy and it was horizontal. And then it had more of exponential models for kinetic energy and gravitational potential energy. And it's really going to be just determined on the rate at which it is changing, right? This can even be seen in our slide, not our slide, but our FRQs that had the slides in there, and it was asking about which would hit the ground first. That was kind of what we were doing, right? The slide that for block 1, when it hit the ground first, that's because its kinetic energy was increasing at a faster rate. And so that means that our kinetic energy would have more of an exponential model. So it's going to be pretty rare that you're honestly going to see an energy graph that's linear. Most of the time it's going to be curved because we just don't normally have just linear models. But that would be how you would do it. You could just see the rate at which your different energies are changing. Okay, let's go and look through the questions. Okay. I'm confused on what to include in my response when doing an FRQ. On the last problem, it included a lot of information and didn't directly ask for. First of all, are you talking about, I know which question you're talking about, but are you talking about like part A, part B, all of them? What are you, what's some clarification here? I'm assuming that for sure you're talking about part A because it was talking about the time it would take to hit the ground. And it may have not like directly asked for that, but that can still be important to even just jot down because you're using it in the next problems, right? That can be something that can be helpful too, is you can use your further problems down the line to see what you can add. It may have not directly asked for that, but if the next questions are going to be talking about the time it takes to hit the ground, that might be something that you might want to include, right? Okay, let's move on to our next. We're gonna do another question. Can we do more FRQs on generally harder topics, deriving especially? Yes, we can do that. And we will also try and do more multiple choice that has like manipulating equations that are not like super easy, I guess. We will try and fit a lot of that into night 5. And on night 5, we're going to be doing like experimental design FRQs, the paragraph response, the qualitative FRQs. We're doing all 4 types to really give you guys a broad depth of everything that we've done. And on generally harder topics, type those in the chat just so that we can make sure we know what topics are hard for you. Okay, the next question says, let's see. I know we haven't gone through it yet, but I know I will need some extra help with torque/rotational motion. That one's a doozy. The biggest thing I would say with that is, honestly, physics, like, it's not like all the units are directly related to each other, but it's really important to realize the things that can be like correlated, right? So for example, like I brought up earlier, your velocity time graph, the area underneath that is going to be displacement, and the area underneath your force distance graph is going to be work done, right? You also have one for torque and rotational motion. Another thing, I'm trying to think of some other things. And also, like, rotational motion has a lot of rotational kinematics, right? We're basically just taking kinematics and putting in new variables to manipulate our equations with variables we're given for rotational motion. Okay, let's see what you guys are saying. Is it time for FRQ or MCQ today? Yeah, it is. We're just doing Q&A. We're not like completely over what we're doing right now. Okay, so what are the differences between gravitational force and acceleration? The formulas are similar. Yeah, but they're different. It's just, those are one of the things that you're just going to have to, like, honestly, I think Shagun was saying this, do not just rely on your equation sheet, right? it's the same thing. Your kinematics equations, there's like 4 main ones, but they're not on the equation sheet like that. They're on the equation sheet as one long equation, and I don't think I've ever used that equation in my life. Let me pull up the equation sheet though real quick to go over that fully, to make sure I answer your question to my best ability. Okay, let's see. You want the difference between gravitational force and acceleration. Okay. Whoa, okay, it's still the same thing. It's just the variables. The formulas are similar, but it's the variables, right? Is it's gonna be gravitational forces due to planets or gravity on Earth? And the masses, things like that. That's just, and also, honestly, if you're really trying to cram in AP Physics, don't do circular motion. 6 to 8% is not going to save you on that test. Focus your time on energy and dynamics. Energy number 1, dynamics 2, and then kinematics, momentum, and rotational motion and torque. Those are going to be your big ones. Simple harmonic motion and circular motion, they're not tested that much on the test. Can we see practice on conservation of rotational momentum? We'll be doing that on night 4 specifically. Night 4 is dedicated to unit 7 because we know that a lot of you guys struggle with it. And then depending on how long it takes you guys to get that down, we will start doing extra review on like past units, or if you guys need to take the whole entire time going over conservation of rotational motion, torque, like we will spend the whole entire time doing that. Okay. So Shagun is going to do a dynamics quiz with you guys now because we did not do one the other night.
Oh yeah, I just put a link in the chat if you guys just want to go to that. Yeah, so the link doesn't work. Okay, let me resend it really quickly. Okay, that should work. Okay, I think we're a little slow on time, so there's like 5 questions on there, so we'll just go until 8 minutes. So we'll see how that goes. So you guys can join after too. So I'll start it now. All right, so it seems that only 4 of you have answered. So yeah, take your time. We're not in any rush here. So just continue with it, even if we get to only this one question by the end. As long as you guys get the concept, then we can continue for that. But yeah, take your time, no rush. All right. There's still like okay, I think if you guys want, all right, I can give you a hint and then I'll give it you like 1 more minute. But essentially what you want to do in this question is first use kinematics to find one of the missing pieces in the kinematics equation, and then you'll have to use that specific value to plug it into the force equation for Newton's second law of motion. Yeah, I think that's the biggest hint I can give you. I won't say what exact value you should find yet, but definitely try to use the kinematics equations. So what I would recommend is just like writing down all the variables you have right now, and then try to look at your formula sheet and then try to see which variables you need to find in order to get from like one step to the other step. Okay, so 26 of you have responded. So we do have 4 minutes of the cram session left, so I'll just end it here and explain this question. So if I reveal the answer, so yeah, the correct answer is A, 16.7 newtons. So let's just break this down, step by step. All right, my computer just froze. Okay, all right. So the first thing we're going to do, if you read the question, it says a 5-kilogram block is being pushed to the right with a force of 50 newtons, and the block starts from rest and reaches a speed of 20 meters per second after sliding 30 meters. Calculate the force of friction acting on the block. Okay, so the first thing I see is that I have my force. I have, what else do I have? I have a speed and I have distance. So force, speed, and distance. So I know that if I use Newton's second of law, or force equal to mass times the acceleration, I have force and I can use a friction force, but I need acceleration. So in order to get acceleration, I need to use my my third law, my third kinematics equation, which is v final squared is equal to v initial squared plus 2 times acceleration times the distance. So here I just plug my values in. So again, it starts from rest. So it would be 20 squared is equal to 0 plus 2 times the acceleration times our distance, which is given to us as 30 meters. So if you rearrange and you calculate the acceleration, your acceleration should be 6.66 or 6 2/3 meters per second. And now that you have your acceleration, you can easily use this for our force equal to mass times acceleration equation. And we know that it's being pushed to the right with a force of 50 newtons. So that's our applied force. And then there is friction. So then we have 50 minus the force of friction is equal to mass times acceleration. And remember that our total system has an acceleration that we just found of 6.66, and then you multiply that times the mass, which is 5, and you equal that to 50 minus force of friction. And then again, if you just use some algebra and plug and chug, you get 16.67 newtons as your answer. So it is a pretty fun question because that you have a lot of involved variables in this, but you do want to think about, there's a lot of ways you can merge kinematics and dynamics. If it's being pushed to the right, 50 newtons, why can't we use F equals? Yeah, well, you can't use F equals ma to find the acceleration, because remember, our entire system includes the force, the applied force, and the force of friction. So in order to find the acceleration of that system, you do need to use kinematics. And we don't have enough information in one equation, because in force equal to mass times acceleration, you only have you have two unknowns, which is the force of friction and the acceleration. All right.
And before we end tonight, guys, I just want to mention, please do the survey for tonight's cram so we can alter things that you guys might have thought we didn't do the best on for tomorrow and the next days to come. It's really beneficial, and by doing that, you guys even have a chance to win $100 to pay for your AP tests.
Yeah. Okay. I do have my work on like a separate piece of paper, which is I can send it later, but I'll add it on to like our Cram hub, so if that helps. But basically, after you find the acceleration, you have to plug your acceleration back into your force equal to mass times acceleration equation, and that is given so your mass is given, you found the acceleration, so you can equal that to the applied force, which is 50 newtons minus the force of friction. You do 50 minus 33.33 because 33.33 is the value, the quantity of mass times acceleration. And then in order to find the force of friction, it's basically 50 minus force of friction is equal to 30.33. So if you equate that together, your force of friction should be 16.67. Yeah, thanks, Yuthi. All right. So it is 10 o'clock p.m. Eastern time, so we will be ending the Cram finale for today. But like I said, I'll post my work if you guys need extra clarification for that. But I hope you guys enjoyed today's Cram survey. Tomorrow we'll be doing a momentum and simple harmonic motion. Night 4 we'll be doing torque, and then for the finale we'll be doing a bunch of FRQ questions. So thank you all for coming, and I hope you had a great night. We'll see you tomorrow.